So thanks for everybody who's still here. So I will start with a small revision of what we did last time. So last time we really started to talk about regularity. And essentially we saw two notions of regularity. For negative regularity and for positive regularity. For negative regularity, in this case we think of distributions, not of functions. Yeah? So we think of distributions. And the way we want to measure regularity is as follows. So we take our distribution, yeah? We test it against the scaled test function, which is centered around the point z, yeah? And which is a support of size lambda. Yeah? And we think of lambda being very, very, very small. Yeah? So this thing here, if u would be actually a continuous function, has to be thought of as trying to evaluate u at the point z. If u is a proper distribution, then this is not quite possible. Then, yes? Okay, so if u is a proper distribution, is a proper Schwarz distribution, so then this is not quite possible. So what you expect is that this thing actually blows up as lambda goes to 0. And can you use your microphone? So last time I used my headphones. Let's see if this works.
Guillermo, can you hear me better now?
Now it's better, yes.
Much okay. It's weird. So much better. Google Meet, I need to take them off, and with Zoom, I need to use them. That's weird. Anyway, again, so when lambda goes to 0, since this is a real distribution and we can't evaluate a distribution at a fixed point, this thing will blow up. And the rate at which it blows up, this is what we consider to be the regularity of the distribution. So this regularity will be negative, right? So here alpha is negative. So actually dividing by lambda to the alpha, you have to think of multiplying by lambda. So actually here we do a multiplication with a certain power of lambda. And when lambda goes to 0, so we multiply by something that goes to 0. And kind of we want to multiply it by exactly this, the good rate, so that it just does not go to infinity. So just as a reminder, so this guy sz lambda eta is what? So here I wrote it down again. So z is a space-time point t comma x. Yeah? And so what we do is the following. We take our test function eta, we center it around the point z, around the point t and x, yeah? And then we kind of blow it up. So lambda is small. So we multiply t prime minus t by lambda to the minus 2 and x prime minus x by lambda to the minus 1. Since eta has a compact support, in order that this is not 0, what needs to happen is that this thing here is of order lesser equal than 1, meaning that t prime minus t is less or equal than lambda squared. Okay. The same x prime minus x must be less than lambda. Since lambda is small, so this function really has a reduced support, which actually goes to 0. And this factor here, which blows up as lambda goes to 0, guarantees that the rescaled version of eta has the same integral as eta. Otherwise, the thing would simply really go to the 0 function almost everywhere. Okay, this is for negative alpha. And now we would like to have a same definition, but for positive alpha. So testing against some function. And you can do this. Yeah? So now if you really have a proper function, continuous function, Hölder continuous function, maybe even differentiable, then you can test regularity in the same way. You take your function u, you test it against a function, and you divide by lambda to the alpha, where now alpha is considered as positive. You want really to measure positive regularity. However, you see that if you do this, take your function u, test against a function, send lambda to 0, divide by lambda to the alpha, then this essentially imposes that your function is 0. Because as lambda goes to 0, u tests against this converges to the value of u at the point z. And since here we really divide by something, this would really mean that u of z needs to be 0. And so this means that the only continuous functions we can have is the 0 function. So since we don't want this, we want to have something that makes sense. What you really need to do here is you need to subtract the first order Taylor polynomials of U. So for instance, if you want to show that U is 1/2 Hölder continuous, for instance, then this PZ would be simply the value of U at the point Z. Yeah. So here, this will give you an integral which is kind of, which contains the point Z and everything that's kind of close to Z. Yeah. So you integrate this function U against this guy. Yeah. So it's something like U of Z prime minus U of Z times something like this. In case this polynomial is simply this point. Yeah. And now this makes sense, right? So if U is 1/2 Hölder, so then this is bounded by Z prime minus Z to the 1/2. And then you can show that all this is really bounded by lambda to the 1/2. Okay, so this was for positive regularity. With this definition, we saw that white noise, baseline white noise, has this regularity. It's minus d12, -1, minus epsilon for any epsilon positive. Yeah. So in space is essentially regularity minus is for each space dimension, you lose regularity 1/2. And for time, you lose regularity 1. Why for time is different? Because we measure distances in time a little bit different. And what we started to do last time is we looked at U that solves this equation, stochastic heat equation, we excise the space-time white noise. And now we would like to figure out the regularity of this. And what I claimed is that the regularity of U is minus d12 plus 1 minus. Where this minus really means, well, it's this regularity minus epsilon for any epsilon positive. So in particular, if you compare this regularity to the one of the white noise, then we see that this one has 2 more regularity than this. Here we have -1, here we have a +1. So kind of this operator here gives you 2 in regularity. Okay. Okay, so this is what we started to do last time. And what we saw is that the one notion is very important, namely the way a kernel blows up at the origin. Yeah. So we saw this definition last time, that we say that the kernel is of order beta if this quantity is finite. And here we need to think of Z being small. That's kind of what for our applications. And in particular, maybe that's more visible, the heat kernel K is of order -d, because what you can show is that you have this inequality. K of Z is bounded from above by Z to the -d. Where here this norm, just as a reminder, is really this. We take the square root in time plus the L1 norm in space. 1 to d to the -d. Yeah. So we saw last time this. Okay. So, and then we did a computation last time. Yeah. So what we would like to figure out is how this behaves. Yeah. So this is what we need to consider to investigate regularity. I introduced a little bit different graphical notation for you, which is this dot and this line here. So make this more clear. This dot with this line, where this dot here represents the white noise, and this line here, the convolution with the heat kernel K. What we saw last time is that the second moment here is equal to, well, to all this expression here. And this is the expression that that we need to analyze. Okay. So then let's do this. So when you look at it, okay, so there are 3 integrals, so this still doesn't look very friendly. And again, a graphical notation helps you. I will emphasize again, you can do this at this stage really without graphical notations. Yeah? But it helps to get already used at this stage to graphical notations. Yeah? So we continue with more graphical notation. We continue with more graphical notation. with more graphic notation. So let's see. How can we represent this? Well, what kind of variables to integrate do we have? We have z tilde. We have z tilde is here and is here. Yeah, to them equal. We have this z1 bar, it's here and it's here. And we have z2 bar here and here. So kind of our graphic notation needs to encode the integration over all these three integration variables. So let's see how I will do this. So here, this will be my integration over z tilde. So z tilde is basically the point that connects the two kernels. Then I have a kernel essentially sitting here, and I have a kernel sitting here. So here they're connected to my z2 bar and to z1 bar. Yeah. And if you want, so here this really represents a k, this really represents a k. And if you want, here we have our test functions. Yeah, so this really represents s zeta lambda, sz lambda eta, sz lambda eta. So let's try to, can I make a zoom? Okay, it's maybe a little bit better. No? Okay. So let's try to have a look at this. So what is happening here? So this line here represents what? It represents k evaluated z1 bar minus z tilde. K at z1 bar minus z tilde. Yeah? This line here represents k at z2 bar minus z tilde. Yeah? Probably the order must be the other way around. So all this here represents essentially this integral. Yeah? The integral over z tilde. Yeah? So this and this stands for our test functions. Yeah? So they're kind of centered at z and evaluated at this point z1 bar and z2 bar. Yeah? So you see, I mean, it looks a bit weird, but it's much faster to write than these three integrals. And you will see at some point that, I mean, the integrals can become even more complicated. And then it really helps to have some nice graphic notation, which kind of shows which kernel or which functions get convoluted with which function. Yeah? So here in this way, we really see immediately, oh, actually there's a convolution happening, namely of k with itself. So maybe the first thing we should do is to try to figure out how this convolution behaves. Yeah? Okay, so this is another nice thing, namely, if you ignore at least this test function, there's a very quick way of having a graphical derivation of this formula. So graphical derivation of star. So basically, I mean, so here I'm ignoring the test functions. So basically what we want to do is we want to compute the second moment of our solution. Huh? So what we see is, well, something like this is happening. We have two copies of it. And what we do, we simply glue them together. Yeah? Of course, you can also write it like this. Yeah? So here and here, I ignore the test function, which are these arrows, double barred arrows. Yeah. So what really this means is that actually what happened is that we glue these two objects together at the head. Yeah. So this means gluing two copies of our object together, gluing two copies of this guy together. And this is great. So once you understand, so I mean, it's yes, exactly. Our goal is to see how the expectation flows up with lambda. And so this is great. Of course, I mean, right now it may seem very confusing, but once you get used to it, a lot of formulas you can derive much faster once you kind of understand the rules that guide these kind of graphical objects. Okay. Anyway, what we see actually is what we need to understand is the convolution. Over here, what we need to understand is the convolution of K with itself. Yeah. Once we understand this, the only thing that is still left is only the integration with respect to the test functions, which are much nicer, of course. They are much less complicated. So this means we need a result. This tells us, well, given two kernels of a certain order, what is the order of the convolution of the two kernels? And this is a computation that you need to do. And I give you the result. Lemma. So let K1, K2 be kernels of order, say, beta 1 and beta 2, beta 1 and beta 2. So these orders can be negative, like in the case of the kernel. Say with compact support. Compact support. If the minimum between beta 1 and beta 2 is larger than the scaled space-time dimension, which is d plus 2, yeah, which I will abbreviate as minus ds. Yeah. So d spatial dimensions and time counts like 2 dimensions. Yeah. Yeah, and beta, which is beta 1 plus beta 2 plus ds, so which is again is beta 1 plus beta 2 plus d plus 2 is negative. Yeah. Then the convolution between K1 and K2 is of order beta, is of order beta. And the norm of the convolution is bounded by the norm of K1 times the norm of K2. Okay. Okay, so you can stare at it for a minute. Okay. Okay, so let's try to understand it, and then I also will write it down. So, okay, so we start with two kernels with certain orders. These orders can be negative. So this would simply mean they have a certain blow up. That's actually our case of interest, right? Because we already know that the heat kernel is of negative order, of order minus d. So then we have two conditions. What is the first condition? We want that the minimum between the two orders is strictly larger than the scaled space-time dimension. Why? Well, simply, if this would not be the case, the convolution wouldn't even be well defined. Yeah. It's like integrating 1 over x squared between 0 and 1. This is simply not well defined. Yeah. So that's the first condition. So remark. So yeah. So beta 1 minimum, beta 2 larger than the scaled space-time dimension, which again is d plus 2, guarantees that the convolution actually makes sense. I mean, not every integral converges, right? So it guarantees that when you calculate the integral defining the convolution, that this integral will be convergent. Guarantees that the convolution is well defined. Is well defined. Okay. The second condition, so that's the first condition, right? So that's the first condition. The second condition, let's see. So we define a beta as the sum of the two orders, beta 1 plus beta 2, plus the scaled space-time dimension. And we want that this is negative. If these two things happen, then the convolution has this order beta, which is negative by assumption. Yeah? And so why do we assume that it's negative? If this wouldn't be negative, then there would be simply no blow up. So I mean, then the best essentially, if this would be positive, the best which this would give this lemma immediately would be order 0. Yeah? So the condition beta less than 0 guarantees, and this is the case of interest, guarantees that that the convolution blows up at the origin. Blows up at the origin. At the origin. At the origin. Okay. So, okay, if beta would be 0, then you still might have a logarithmic blow up. Then one might have a logarithmic blow up. Might have a logarithmic blow up. Blow up. Okay. And okay, so I'm not sure if I'm good at giving you heuristics why the order of the convolved kernel is beta 1 plus beta 2 plus ds. But so you need to think of the case where beta 1 and beta 2 are negative. That's our case of interest. So while you have two kernels, I mean, when you have a convolution, you integrate a certain product. Yeah. So then it makes sense that, so you take a product of one function with order beta 1 and one function of order beta 2. So it kind of makes sense that the orders kind of add up and they get worse. Yeah. But then there's a volume factor that kicks in and where you gain actually a little bit, right? I mean, it's like when you integrate 1 over square root of x to the 1/2, yeah, in one dimension. So this gives you x to the 1/2. Yeah. So you're kind of, because of this integral, the minus 1/2 becomes minus 1/2 plus 1 if we're on one dimension. Yeah. So that's really the same. That's what happens here. Okay, other questions? Okay, so then let's continue. So where did we stop? So we stopped essentially here. We want to evaluate all this integral. And the first thing that we will do is evaluate this integral, or not evaluate, but estimate this integral. Yeah? So this integral is over z tilde. So we need to compute, and what is this here? That's really a convolution between the two curves. Yeah? So probably I messed up here with the signs here. So really what we want to do, so we want to estimate this convolution. Yeah? And so we can use our lemma. So we just need to check the assumptions of our lemma. Yeah? Yeah? So we continue. So again, so we have something like this. And here are our test functions. And so this thing here really is convolution of K with itself. Yeah. So let's apply our lemma. So we apply our lemma. We apply the lemma. The lemma. So let's see what we need to check. So what were the conditions? So the first condition was that the minimum of the orders of our kernels must be larger than minus d plus 2. Okay. That's the first thing. Here K1 is equal to K2. Yeah. So here, actually, the orders are the same because it's the same kernel. And we already figured out that the heat kernel has order minus d. And this is larger than minus ds, which again is minus d plus 2. So this is fine. This was the first condition. So the second condition, which kind of then tells us what is the order, it says that beta 1 plus beta 2 plus the space-time dimension must be negative. Okay, so let's try to compute this. So, and well, beta plus beta, which is beta 1 plus beta 2, plus ds is minus 2 times d, yeah, plus d plus 2. Yeah. So let's see, what is this? So 1d cancels. So this is 2 minus d. I hope you agree. And so this is negative if d is 3 or larger. Okay. So in this regime, we actually can use the lemma. Yeah. So hence, if d is larger or equal than 3, so what we can do is, well, so here we have our convolution, right? So here we have our test functions. And really what is only important is to know the orders. So what this lemma implies, that actually integrating over this variable here gives us a new kernel with order 2 minus d. Yeah. So again, all I was doing is estimating this integral, yeah, which corresponds to this black dot here, or white dot actually, with this filter. Okay. And this is great. So because now one can use the following observation, something I will not show, so you can try to check this. Yeah, that if I have this double integral s z lambda eta, let's say z1, s z lambda eta, let's say z2, times z1 minus z2 to some power beta, this is less or equal than lambda to the beta. This is a computation that you can try to. Yeah? And so now what's happening here? So here I was saying that this convolution, okay, I can do this convolution. This will give me a certain kernel. And this kernel has order 2 minus d. Yeah. So in particular, I can replace. So here, what we really do, replace, say, k convolved with k of, let's say, z1 minus z2. By what? Well, by z1 minus z2 to the power 2 minus d. this is what this inequality allows me to do. Yeah. So at the end, I really need to estimate this where beta is 2 minus d. And this gives me exactly the estimate I want. Thus, if d is at least 3, this expectation s that lambda eta squared is less or equal than lambda to the 2 minus d, or minus d plus 2. Which is, another way to write this is we take a second moment, so this is minus d half plus 1 squared. Right? So now let's return to see what we actually, yes.
So in the graphical notation, kind of the test functions doesn't have an influence on the regularity.
No, they're like regularity 0 if you want.
Okay, and there is a simple way to see this observation.
You need to do the calculations. Okay, at some point I didn't do for a long time, but there may be some kind of change of variables argument.
Okay.
Yeah.
Okay, I believe you.
Okay, but it makes sense. Why does it make sense? I mean, if you remember, okay, actually, I have it written down. That's good. So in this with So with this definition, we kind of test how things blow up, right? So we take this test function. This kind of really tells us how things blow up. Now, if you have like z1 minus z2 to some power, and this power is negative, well, this blows up to a certain power. And so if this definition is a good definition, then it really should give you the right order in lambda, or the right exponent in lambda.
So the order of the kernel coincides with the regularity if you see the kernel as a distribution.
Exactly.
So basically this.
Exactly. Yeah. Okay. Great. So let's see. So what did we want to show actually? We wanted to show this. And that's exactly what we showed, at least in dimension 3 and higher. Right? Minus d half plus 1. What do we have here is estimate minus d half plus 1. And this 2 is because we have a second moment here. Yeah? And now, since you use Gaussian, you get essentially the same estimate for all higher moments, where the 2 would be replaced by a p. Okay. If the dimension is 2, what do we want to show? If the dimension is 2, if this would be 2, then this would be 0 here, which stands actually for some kind of a logarithmic blow-up. So in this case, you essentially still can apply the lemma, but with some kind of logarithmic blow-up. So in a sense, in dimension 2, you can still use this lemma, but you get a logarithmic blow-up. So I will not show the details. But so if d is 2, so we still get a logarithmic blow-up as desired somehow. Blow up as desired. Okay.
And for d equal 1?
For d equal 1, I mean, so you see, if d is equal to 2 in this condition, this is exactly 0. And then you can always pretend, well, okay, so minus d is kind of the optimal order of my kernel. If something is of order minus 5, it's also of order 6, minus 6. So you can then pretend of order minus d minus epsilon, then it's fine. You can use this lemma. In d equal to 1, I mean, this horribly fails. This simply fails. I mean, this lemma you simply can't apply. There's no way of applying this lemma d equal 1 and getting some sensible result. Of course, you can always pretend that the order is not minus 1, but minus 3 in dimension 1. Then you get simply the wrong thing. And there's the reason for this. in d equal to 1, what do we want to show? And I will not do the computations in detail because otherwise we lose too much time. In d equal 1, what is this? This minus 1/2 plus 1. It's plus 1/2. In d equal to 1, we want to show positive regularity. So we're looking at the wrong object. Let's see.
Because this is just a usual SDE, right?
Well, it's
I mean,
SDE, but the object is the solution would be still something regular. It's a function.
I see.
So you see, this definition is the correct one if the regularity is negative. But if the regularity is expected to be positive, I mean, like 1/2 Felder, for instance, then we want to do something like this. We want to look at these kind of differences. So we need to kind of to subtract the Taylor polynomial here in the definition of variety, something that we didn't do. So there was no way of getting the result in d equal to 1 with the computations we did, simply because it was the wrong thing to do anyway.
But my point is that for d equal 1, the Laplacian is just okay, it's still a PDE, but the white noise is just the derivative of the Brownian motion, no?
No, I mean it's still space-time white noise. So if
okay,
space.
Okay.
Okay. So if d is equal to 1, this does not work. And I will not give the details. This does not work. But again, but we want to show that U has regularity 1/2 minus. So when I write this minus, this means it has not quite regularity 1/2, but a little bit less. So positive regularity. Hence, we want to look at terms of the form, look at terms of the form say u of z minus u of z bar. And what we want to show is that this is something like z minus z bar to the 1/2. That's really what we want to show. Yeah. Yeah. Hence, we look at the wrong object. Hence, we look at the wrong object. At the wrong object. Yeah. So I hope this is clear.
But I imagine that's not much harder than.
No, it's not much more harder. So then you need to deal with derivatives of the heat kernel. So there's a slight trick that you need to do, some tail expansion, but it's the same spirit. Yeah.
Okay.
So object to look at is the following, and I will not do the computations because we need to go forward, is u minus u of z tested against this test function. Yeah. This is what you need to look at. Yeah. And in this case, well, you need to work a little. So you can repeat some of the computations I did, and then you will see differences of heat kernels. So you see. Here, I have the product of the heat kernel, and then you will see product of differences of heat kernels. And then naturally, you can kind of estimate them by the derivative of the heat kernel, which is a lower regularity and lower order. And then you're again in the framework of the lemma. Of this lemma. Yeah. I will not do the computations. Then the notes, so you can have a look at it. And I will kind of stop this computation. But do you have any questions about this? So what we proved in the case of white noise actually is a general phenomena. This is something that's called Schauder estimate theory. It's called Schauder estimate. This is one of the central points in this theory. Yeah. So for F in these C alpha spaces, define U of S X as following. So it's the it's the integral from 0 to S, the integral over R, D, or over the torus, it does not really matter. K is SR, X minus Y, F of R, Y, dr, dy. And if F is a distribution, then you need to interpret in the correct sense. Yeah. Then, if alpha is not an integer, so these integer values are always a bit particular. Yeah. That several ways of defining these C alpha spaces, they always give kind of a problem. Yeah. Then the norm of U in the space C alpha plus 2, yeah, is bounded by the norm of F in the space C alpha. C S alpha. What this means is that U is in CS alpha plus 2. Yeah. Yeah. So taking the convolution with the heat kernel with this function K improves regularity. So this guy is a friend in this game. Yeah.
Can you repeat the problem with the alpha integer?
Yeah, so if alpha is integer, so then usually these kind of theorems break down a little bit. If you also think a little bit about it, for instance, alpha equal to 1, so what is C1? So either you can say, well, these are contingent differentiable functions, and this is actually not what is done here. For C1, this would be kind of Lipschitz continuous functions, right? So actually for C1, you have kind of at least two definitions that make sense, but the way we do it, you only would have Lipschitz continuity. So these integer values are always a bit special.
Even for negative values.
Yeah, yeah.
Like -1.
Yeah. Yeah, but in practice, that's never a problem, actually.
Okay.
Okay, and so again, so the reason I just want to emphasize, the reason that we gain 2 is, well, the following. So first of all, we're in this scaled space where time and space are treated a bit differently. Yeah. We have, for instance, a Laplacian then equation. So we need to be able to do 2 derivatives in space. So hence in space, we gain 2 of regularity. We have a first derivative in time there. So we need to be able to do 1 derivative in time. So this kind of implies that the solution must have 1 more regularity time than the noise, than the right-hand side we started with. Yeah. And since time counts double somehow, this 1 of regularity in time is like, counts like 2. Okay. So that's it about the linear equation. So now let's get back to our nonlinear equation. So nonlinear equation. So of course, in this case, we don't have really an explicit solution. I mean, in the linear case, this is really the explicit solution in case the initial condition is 0. Otherwise, you need to add it. So that's really explicit, right? So F is given, you know K. So it's really completely explicit. Of course, in the nonlinear case, it's not that explicit. So just as a reminder, this KPZ equation, yeah, was this guy. ETHTX is the second derivative in space, so it's one-dimensional here, yeah, plus the derivative in space squared, yeah, plus psi of Tx, yeah, where T is positive and X, say, is not torus. Okay. Okay, so let's try to solve this guy. And there's the way which is called mild solution or Duhamel's principle. So, which gives us kind of an idea how the solution needs to look like. So let's use this. Okay, Duhamel says that this solution must be what? Must be the integral between 0 and t, must be the integral in space of k of t minus s, x minus y, psi, say ds, dy. Okay, so that's the same as in the stochastic heat equation. But then we still have this guy here, so we need to integrate this guy. So plus integral in time, integral in space. You can write it a little bigger. Integral in time, integral in space, k of t minus s, x minus y, and then you have this derivative here, s, y, ds, dy. Yeah. So this would be the mild form of the solution. Why is this mild form of the solution great? Because it kind of tells you how to set up the fixed point problem. Okay, and this is what we try not to do. So we try to solve this fixed point problem. And the first observation that we have, I mean, this guy, we just investigated this guy. We know its regularity. This T here is the torus. So again, so this guy we just investigated, we know its regularity. Yeah? So by Schauder, or by our calculations, yeah. So this guy here, k of t minus s, x minus y, psi ds, dy is in which space? Well, it's in the space CS, and let's say C. The space dimension is 1, so it's -1. The time dimension is also 1. So this is now the regularity of psi. The regularity of psi. But now we learned by Schauder that actually taking the convolution with the G kernel improves the regularity by 2. So we can add 2 here. And okay, we never completely like this, so it's a little bit less. So doing the calculation. Yes.
Sorry, we can use the graphical notation, right, for this integral?
Sure, it would be like this. We will do this in a minute. More than you like, probably. Okay, so this is what Schauder implies. So now what we probably would like to do, we would like to set up a fixed point problem. So when you want to set up a fixed point problem, you need to define a fixed point map, right? So a map that maps a Banach space into itself. Yeah? And then you try to, I don't know, show that it's a contraction, and this implies there's a fixed point, and this fixed point is the solution to your equation. Yeah. So there's essentially only one choice for a fixed point map. So let's define a fixed point map. Point map. So how do we do this? Well, would be like this. Psi of h must be what? Well, our solution must be what? K convolved with psi. Okay. K convolved with psi. Plus, let's see. K convolved with dxh squared. So this should be the other ingredient of our fixed point map. Plus K convolved with dxh squared. So this is our fixed point map. If it has a fixed point, it solves our equation. Okay. So the first task is to find a nice space on which this fixed point map acts. Such that it maps the same space, the space in itself. And well, essentially, there's not so much choice because this guy here has regularity, let's say 1/2 minus. Yeah? So that's a natural space. I mean, it's better to define psi on a space that has as much regularity as possible, because then you have nicer objects to work with. So it's essentially the best you can do. So what's the ansatz? Define psi on CS 1/2 minus. Yeah. Okay. Cool. So what we hope is that if H has regularity 1/2 minus, the psi of H has the same regularity. Let's see. K convolved with psi, great, has the perfect regularity. So what we need to understand is this here. Okay. So if H has regularity 1/2 minus, so then this is something you can show, its derivative, which of course only exists in the generalized sense, has regularity 1 minus 1/2 minus. Yeah. Okay, so this you can show. There's no problem. So now the natural question is the following. So in which space is the square of this if dxh has regularity minus 1/2 minus? Yeah, that's a fair question.
Oh, but then that is where the problems begin, right?
Exactly.
Because we don't know right now how to define the product of two distributions.
Exactly. Exactly. So as Guilherme said, the answer is, well, there's no space because this thing doesn't even make sense. And this is a result. It's a theorem. It's a fact. So theorem. So, I mean, we want to define this product, and of course, this product should be kind of reasonable. I mean, you can define anything and call it a product. But if you want it to be reasonable, then there's a problem. So, theorem. Suppose that you have two regularities, alpha plus alpha and beta, and they add up to a positive number. So then there exists a bilinear form, a B, there's two entrances, acting on CS alpha and CS beta, yeah, mapping to the minimum of alpha and beta, okay, such that, first of all, for F and G is smooth, this bilinear form is the usual pointwise product between two functions, nothing spectacular. You take the product as you always do it. So B of F G is equal to the pointwise product. Pointwise product of F and G. Yeah. 2. So for really functions F or distributions F in C alpha and G in CS beta, yeah, what you have is that this bilinear form is continuous in the space alpha minimum beta. So it's less than the norm of F in C alpha and the norm of G in C beta. Space. I hope it's still kind of readable. If not, I can rewrite it. But so all it says, if alpha and beta add up to a strictly positive number, then you can define this bilinear form where for smooth function, the bilinear form is the pointwise product. And this thing actually turns out to be a continuous map. So you can extend it really to this full space. Yeah, so there's a continuity condition. So this means that the product between two objects where one of them is possibly a distribution, you can approximate it using the product of smooth functions. Yeah? So now the
sorry, so you can prove this via approximation.
No, well, this thing's, yeah, so this simply says that, let's say f is a distribution and g must then be a function. That then the product between these two can be approximated by the product where you take kind of smooth functions.
I see.
Yeah. So you can write it as a limit of something that you know how it works. So now the question is naturally, what happens if this is not true? Then the result is, then this is not possible. Such bilinear form simply does not exist. Yeah? So if alpha plus beta is less or equal than 0, then no bilinear form exists. Form exists. Yeah. And this is a problem for us. Yeah. Why? Because, well, dxh has regularity -1/2. So if you sum it up, -1/2 plus -1/2 is -1. It's nowhere close to 0 or something positive. So in particular, this thing, there's no way, a priori, no way of approximating it in a smooth way. And this maybe also explains that the result I was presenting in the first class, that there's this kind of renormalization constant that goes to infinity. So there's no way of approximating this in a smooth way. Yeah? So there's no canonical way of defining this. So this object simply does not exist in a sense. Yeah? It's what this result says. So this result doesn't say that, well, if you try hard enough, maybe you could succeed, but the result is actually worse. It says, well, you don't succeed. We can prove it. Yeah. Conclusion. There's no canonical way. And canonical means in a reasonable way so that you can really approximate in a smooth way. There's no canonical way. Canonical way to define the product. Yeah. So it is not clear how to solve the fixed point problem. It is not clear how to solve the fixed point problem. Fixed point problem. Point problem. Okay. Are there any questions? Okay. And of course, because of this problem, stuff like regularity structures exist. And now we really will delve into it. Yeah? So this was a little bit the linear theory. Now we really go to linear regularity structures. Okay. So regularity structures. Okay. So maybe you remember the result. Recall. So if you look at KPZ, I mean, we don't know how to solve it, but there the x squared. There's this result by Heira, which says something like this, which I mentioned at the beginning. Minus c epsilon plus xi converges. It was something like this. Yeah, I will not write down the full result. Just recall that this constant c alpha, c epsilon, these are constants, deterministic constants, but they go to infinity when epsilon goes to 0. What this, of course, shows is that so what we do here is we take a smooth version of psi, a smooth approximation of psi. So this means that the KPZ equation, it's not a continuous equation as a function of the noise. It's not a continuous function of the white noise or of the noise Yeah? So then there's a natural question is, well, of what is the continuous function? So what would we need to know in order to formulate it kind of as a continuous function? So maybe it's not enough that psi epsilon converges to psi, but what if we would know a little bit more, not only the psi epsilon converges to psi, but maybe we know some additional properties. Could we then pass to the limit without any problem? Yeah. Of course, we couldn't recover white noise because I mean this result is what it is. Yeah. But you could imagine to approximate different noises that are a little bit better behaved. So what would you need to know about the sequence of approximating noises so that you can naively pass to a limit in the equation? This is the big question. And so for this, you need to know the structure of the equation. How can you kind of extract information about the structure of the equation? Well, you can make a PK iteration. Yeah? Then you get kind of an idea what kind of terms are in the possible solution. So what you would need to control somehow. Idea? We do a naive PK iteration. So we ignore all the problems that could appear. Yeah? And we start with a naive PK iteration. So what I will now do now in the next few minutes is kind of try to explain a little bit the philosophy of regularity structures. Then we will come to our first definition. And if there's time, I will give you a concrete, simple example, namely how polynomials fit into this framework. Of course, we don't want to study polynomials, but it's again an object that we know that we understand better than the singular SPDs. But I would like to tell a little bit of philosophy of regularity structures. It may not be also clear, but maybe you get some idea. So let's do a PK iteration and ignore all the problems that there are. So maybe H00, okay. So H1 is psi of H0. Yeah. So what is this? Psi was defined here. This map. So in particular, H is 0. Okay, the derivative of 0 is 0. So this term vanishes. Okay. This term vanishes. So this is really just K convolved with psi, which we write like this, right? That's the first step in the PK iteration. Second step, H2 is psi of H1. Of course, if this equation would be smooth, then this procedure would converge. So what is this? This is K convolved with psi, right? This is how psi is constructed. This term we always have. And then we need to take the derivative of our input, square it, and convolve with K. So we need to take K convolved with derivative of the input and square it. Yeah? So let's introduce more graphical notation for it. Yeah? This K convolved with what? Well, when we write this line, this means convolution with k. So we need to have something else for convolution with the derivative of k. So you can convince yourself that when you calculate this, then it's the same as taking convolution with the derivative of k. So this thing here is convolution with k prime. With dxk. Yeah. So then a nice graphical way is this here. So you essentially have two copies and they go together here. Yeah. So again, so there's some kind of a new notation I'm introducing, and it is not super important for what comes, but it's good to get used to it. And here you have this, right? So what it really means is we take psi, take the convolution with the derivative of k, yeah, then we square it. This is this. So we take this times this up. So this gives something, and of this something we compute the convolution with k. It's this. Okay. And now you can continue. Yeah. Now you can continue. So now we can define an H3 with a psi of H2. Yeah. You now do the computations, and then you get something of this form. This term that you already had, something like this. Yeah. And then you get all sorts of terms. Something like this, and this gets doubled. And convolve with k, and then there are more terms. Okay. So this is when you kind of proceed. Of course, here at this stage, I was pretending that I'm allowed to do this. If I'm dealing with a real solution, then we saw that this operation is already not allowed. Yeah. The point of view of regularity structure is now the following. It says the following. Well, okay, if I do a naive Picard iteration, something like that I obtain. So if there's an object that is a reasonable candidate for the solution, it must have this form. It must have this form. There's no other way. But now, of course, there's a problem that well, some of these objects don't even make sense. If the solution exists, the solution must have an expansion of this form. Problem, for instance, this may not make sense. The idea is now the following thing. Well, let's split the problem into two parts. In the first part, we pretend that there's no problem. Yeah? In the first part, we think of H being of this form. So that's the point of view of regularity structures. Point of view of regularity structures. Regularity structures. So what we do, we consider expansions of the form, consider expansions of the form say h of z is equal to maybe something which we don't know. It's an unknown. Maybe you draw this in yellow. Times this plus maybe h of this times this object plus maybe h of this kind of complicated object, which you don't need to understand really what it is. Takes more time to draw them. This, and maybe more. Yeah. So we consider expansions of this form. In the first step, we pretend that all of these objects, they simply exist and they're like basis vectors. Yeah. So solutions to this equation, we can always express in forms of the spaces. Yeah. And then of course, in front of the basis vectors, they are possibly functions that depend on Z or not, depends. Yeah. So that's the first step. We pretend there's no problem with all these objects. Yeah. So we consider them as fixed basis vectors. Yeah. And now we look at all functions that can be expanded in terms of the spaces. Yeah. This gives a certain space of functions. It's called D gamma space. We come to that later. And maybe in this space, we can formulate a fixed point problem and try to solve it. So then we find these guys. Okay. Okay, so maybe this works. But of course, I mean, there's still this problem. At some point, we need to face the fact that these things don't exist. Yeah. And the second step, we do this. And this is purely stochastic work. So the first work is purely analytical algebraic. And the second step is purely stochastic. Because all of these objects, they can be expressed in terms of convolution of heat kernels. Yeah. And they don't necessarily converge. They don't, actually. But then there's something called renormalization. So you can kind of, there's a kind of a stochastic procedure which allows you to analyze, for instance, this guy and to understand better why it does not converge and kind of to try to take this part out. And this all lands in the renormalization constant. That's kind of the idea. Okay, let's write down the observations. So, okay, no, maybe not. Otherwise, I don't get anything done. Yeah. So again, in the first step, we assume that all these objects are given. Yeah, and we consider the space of all functions that can be written in terms of the spaces. And the second step, we use concrete stochastic calculus to kind of to cure the divergences of these guys. That's kind of the idea. And it's kind of fascinating that by kind of pushing the problem of non-existence of these guys in the first step away, it kind of works. Guilherme.
Is where a Vic product will appear to give sense of these objects.
Where what will appear?
Vic products.
Exactly. So that's I mean, this is nothing Haider made up. So that's kind of a more or less well-established theory of so-called Vic products, kind of renormalized products, which you can use here. Yeah.
But somehow you. I know. Okay, maybe you are going to explain to us. So,
what exactly? So then I can.
I mean, the procedure to approximate this, to give a sense of this, is kind of you approximate each. Let's suppose you want to make sense of the product.
Mm-hmm.
We approximate each part of the product,
mm-hmm.
and we subtract something that depends on the Vic product.
Exactly. Yeah,
I see.
Yeah, but I will still try to explain. Yeah. Okay.
I have the question.
Mm-hmm.
This formal expansion, when you, in order to get this formal expansion, you look at the equation with T epsilon, no?
I look at this equation with
the constant C epsilon.
Yeah. So this okay. When I look at the expansion, so that's the kind of the nice thing. There's something called regularity structure, which I will define in a moment. And there you don't see any epsilons, any constants. It's kind of fixed things. So these basis vectors are fixed. And then there's something called a model. When you apply the model, there you put in the epsilon dependency, and that's where this kind of constant C epsilon appears.
Is this the reconstruction theorem?
Has also something to do with this. Yeah, but yeah. Okay, so the model, I mean, I will still define this. The model kind of turns these abstract guys into concrete guys. They're completely concrete. So you can write down integrals, convolutions. So they're completely concrete. And then what this reconstruction theorem does is, well, first of all, we consider them as basis vectors. Yeah? And then we formulate a certain fixed point problem for all functions that have this expansion. We solve this fixed point problem, okay? But then the problem is, okay, we can solve it, but then we still need to say what it has to do with our original equation, because an original equation with concrete object. And the reconstruction theorem takes kind of the solution to the equation, some kind of a weird space, and maps it down to a very concrete object, which is really the solution we are looking for. But this is all.
The C epsilon you choose in the a posteriori.
Yeah.
After the normalization procedure.
Exactly. Or during the renormalization procedure, you construct the C epsilon.
Okay.
So the C epsilon in the sense is, so you see, maybe this does not converge. So you need to subtract something. What you need to subtract goes into C epsilon. Maybe this still doesn't converge. So you need to subtract something. And this part also goes into the C epsilon. And then you add all these things up, and this is the C epsilon.
Okay, thank you.
Okay, so let's start with this. So now I will give the definition of a regularity structure. And maybe I start to explain. Yeah. We'll look at the first concrete example of a regularity structure, which has nothing to do with SPADs, but only with polynomials. So definition. So a regularity structure. Capital tau consists of a triple A, T, and G, where 1. Yeah. A is simply a subset of R. Yeah. Is an indexing, it's an index set. Which is bounded from below. Is bounded from below with no accumulation points. Bounded from below with no accumulation points. Accumulation points. Okay. So what is this A? Well, as I wrote, it's an index set. And so you see, when we started to do this PK iteration for the KPZ equation, so what you kind of imagine is that maybe there's some way of, for instance, so this guy, so that this really stands for some like convolution of psi with the heat current. This is a certain regularity. This regularity would go into the set A. That's one of the indices. Maybe this guy has another regularity. This number, which is a number, some number alpha, would also go into the set A. This guy maybe also has a certain regularity. This number would also go into set A. So this set A is simply the collection of all the regularity or homogeneities you will end up observing when doing this expansion. Nothing more. 2. T is what is the so-called graded vector space, which is a direct sum over all alpha in A of T alpha. Yeah? It's a graded vector space. Vector space. It's a graded vector space. And each T alpha yeah, is a finite dimensional space, finite dimensional space. It comes with this norm. It comes with the basis and norm. And norm. Of course, if it's finite dimensional, then you can choose whatever norm, right? They're all equivalent. So that's T. What is T? What is T alpha? So T alpha, in a sense, you can, in T alpha, you collect all the elements of order of homogeneity of regularity alpha. Yeah? So this guy, for instance, in dimension, this guy, for instance, dimension 1 has regularity 1/2. So then this guy would be an element of T 1/2. Yeah? Psi has regularity -3/2 in dimension 1. So psi would be an element of T -3/2. Yeah? So you write simply down your order kind of in your spaces, the elements by order. And 3, and this is something I will not comment yet. G is a family. It's a family of linear transformations. Transformations on T, such that for all elements in G, and for all alpha in A, and for all tau in T alpha, we have that gamma tau minus T alpha is in T alpha minus, where T alpha minus is simply the direct sum over all beta, strictly less than alpha of T. Okay. And finally, moreover, we require that G forms a group. That we require that G forms a group under composition. Forms a group under composition. Okay. So these are the 3 elements. I will not comment it on G. So we will see G much more concretely in example. Then I hope we understand better what it is. And here at this point, I have to admit that probably G is the object I understand the least yet. Okay, so again, so regularity structure has really 3 objects. A is an index set. T is it's a vector space, and you kind of can order the T into its different T alphas. When each T alpha, you have the elements of order alpha. And okay, G is a group. So what we always will assume is that 0 is an element of A. Always assume that 0 is an element of A. Second, so for, I already said this, but I will write down for alpha and A and tau and T alpha, we also say that tau is an object of order alpha, that tau is an object of order alpha. Of order alpha. And in this case, we write this. So this really means that tau is an object of order alpha. and we denote by tau alpha its norm on T alpha. Okay. And finally, so Q alpha denotes Q alpha is the projection on T alpha. Denotes the projection on T alpha. On T alpha. Okay. So are there questions? Okay. So what I will do now in the last minute, so I don't have much time, and essentially I will give you an example, and we will continue on Monday this example. Namely, there's a very standard regularity structure, which is the regularity structure of polynomials. So simply meaning that polynomials, normal polynomials, nothing fancy about it, we can reformulate in terms of this new framework. And that's what I would like to do now. I would like to start with this now. And then on Monday, we will see how we can use all of this to measure regularity and all this kind of stuff. Yeah? So regularity structure of polynomials. So that's an example. Of polynomials. Okay. Okay, so what do we need to define? So let's check in the definition. So a regularity structure by definition has three elements, A, T, and G. So let's focus on A. So A is an index set which is bounded from below with no accumulation points. Okay. In the case of polynomials, it's relatively easy because what is A? A is just an index set, so it should kind of list all the different orders that can appear. So if we speak about polynomials, well, can have zero order polynomial, first order polynomial, second order polynomial. So x squared is a polynomial of order 2, x cubed is a polynomial of order 3. So in this case, this index set is simply n. That's the first ingredient. The second ingredient is T, yeah, where T is this graded vector space, yeah, and essentially contains really the elements that we have, that we want to consider. So T should then be really all the polynomials, right? So this should be really the polynomials. And now you know you can have polynomial in 1 dimension, 2 dimension, 3 dimensions on certain indeterminants, yeah? Indeterminants. I think that's the word. Right. Say x0, x1, x2 until xd. Right? Where this x0 we imagine is like the time direction. Yeah. So x0 encodes time direction. Time direction. Okay.
But is it important to be a finite number of indeterminants, or can be?
No, we would like to have a real a normal polynomial. So it should be finite, yes. And because this is really, you see here, it's our equations are formulated in space time. So R times RD, R times RD, right?
Okay, so okay.
So don't make it more complicated. I made this already. Okay, so that's T is really all the polynomials that you can imagine in these indeterminants. So what else? Let's go back. Aha. So we need to be able to write T in this form. So we need to define what is T alpha. Well, T alpha will be all polynomials of order alpha. Yeah. T alpha. So will be all the object of this form. So over sums over K, where Ks is equal to alpha of AK x to the K, and AK, well, it's a collection of real numbers. Yeah. So reminder, maybe you forgot it already. So for K0, K1, up to KD, so we write Ks is simply the sum. So wait, so this is an element of n to the d plus 1. We write this as K0, no, 2 times K0 plus K1 until KD. Yeah. And x to the K is x0 to the K0, x1 to the K1 until xd to the K. Yeah. So here really we have polynomials of order alpha. I hope this is clear. This is a T alpha. So now, I mean, you can convince yourself that whatever polynomial you can imagine, you can kind of write it as a sum of elements of the difference elements of these spaces. Okay. Okay, so last point, and then we stop. G, so ATG, right? There was ATG. So G is a family of linear transformations on T. That's for gamma and G, alpha and A, tau and T alpha. Gamma tau minus tau is in tau alpha minus. Okay. In this case, what will be the gamma be? The gamma essentially takes a polynomial, and a polynomial can be centered at a certain point, maybe an expansion around the point 0, around the 0.5, whatever. And the gamma kind of will shift this point of expansion of the polynomial. That's all the gamma does. And next time we will really see why this is kind of an interesting thing to look at. So what we will see is that the definition of C alpha spaces we can write actually in terms of a regularity structure. Yeah. So each gamma in G is of the form gamma z prime, where this guy is what? Well, gamma of z prime applied to x to the k does what? It kind of recenters the polynomial. Minus z prime minus z to the k. Yeah. So this guy centered the polynomial at z prime minus z. Polynomial at z prime minus z. So that's what it all is. So you can check that it really satisfies the condition of the definition. And next time, to start with, what I will show you is how you can encode smooth functions in this regularity structures. And essentially, I mean, what we do is next time at the beginning, at least, stuff that you all know, yeah, but kind of creating this new framework. Okay. So kind of we will see again the definition of the C alpha spaces, this time maybe in the classical sense, but we kind of will see how we can formulate it using this regularity structure. Yeah. And then, of course, we also need to go to regularity structures of SPDs. Okay, so I guess I will stop here. It's already late enough. It's Friday.
I have one question.
Mhm.
Is this the natural choice for the group for the KPZ?
This, no. I mean, that when you go to SPD, it's getting more complicated. So the thing is, when you go to the regularity structures of KPZ or SPDs, one part of this regularity structure is the regularity structures of polynomials. You still want to keep them, but you need to add more things, and then this gets a bit more complicated.
You also need to add something more to the group.
Yeah, exactly. Yeah. This is actually the part. So the nice thing is that there's actually an algorithm that does it for you. There's some kind of automatic procedure. This is the part that I also don't still understand so well. But so next year, hopefully in Sao Paulo, there will be a school of a guy who studied actually this structure group quite a bit.
Nice.
Any other questions, comments?
Maybe Guilherme, just one comment. So in the notes, I don't remember, it's chapter 3 or 4. So they don't look at KPZ, but so-called 542 and 542 equation. And there they derive the form of gamma in a certain example for 542, I think. Because there's some restrictions on gamma. And when you work out all these restrictions, you can then compute what it must be.
Nice. Will we have time to see particle systems?
No.
Okay.
No, so you see, it's now so maybe I'm too slow, but it's now the third lecture, and now we start to talk about regularity structures. No, unfortunately not.
Next time.
Maybe, yeah. But then one is not allowed to do, I think, all the stuff of linear SPDEs and short SPDEs. Then you need to assume it, I guess.
Okay, thank you. We continue on Monday, no?
Mm-hmm.
See you Monday.
So
Thank
have a
you.
nice
Bye-bye.
weekend.
Bye-bye.
Bye.